Dr. Steve Croft is an astrophysicist and educator specializing in the search for technosignatures, indicators of technologically advanced intelligent life beyond Earth. He's primarily based at UC Berkeley, but is also a senior research fellow at the University of Oxford, UK, and an adjunct senior astronomer at the SETI Institute in Mountain View, California. Steve is project scientist for the Breakthrough Listen initiative, the most comprehensive technosignature search program to date. His responsibilities include directing Listen's multi-million-dollar observational program on the world's largest steerable telescope, the 8,000-ton Green Bank telescope. Steve is also the director of student research at the UC Berkeley SETI Research Center, leading an award-winning program that engages top-flight undergraduate students in cutting-edge astronomy research. Over 140 program alumni are working at some of the top academic institutions and tech companies. Steve has also personally supervised dozens of students in undergraduate and graduate research. Steve has also been awarded time on the Spitzer and Hubble Space Telescopes, authored over 100 articles in scientific journals, and in addition to serving on review panels for NASA and the National Science Foundation. He has been interviewed by numerous media outlets, including The Observer, The Economist, Space.com, Science Channel, and more, quite the laundry list, and has written press releases, and popular science articles for public audiences. He also serves on the International Program Committee for the International Astronautical Congress, and is a member of the editorial board of the International Academy of Astronautics Journal, Acta Astronautica. Steve grew up in England, where he obtained his undergraduate degree in astrophysics from University College London and a PhD in astrophysics from Oxford University in 2002. After postdoctoral research at Lawrence Livermore National Laboratory, he then moved here to UC Berkeley in 2007. Currently lives in Oakland with his wife Lori, a lawyer, and their dog Laika. So we are very thankful to have Steve here today, who will be telling us all about Breakthrough Listen. Please take it away.
Thanks for the opportunity. I sent a long bio and sort of gave you guys the option to edit it down, but I guess, sorry for the sort of long laundry list there. The dog is named after the first dog in space rather than the camera brand. I don't know why people think I have a dog named after a camera brand, like the space dog. I'm going to tell you a little bit about what we're doing with Breakthrough Listen, and yeah, here we go. So people have been asking themselves the question, is the life beyond Earth, really, since I think they first gazed up at the stars and sort of wondered what's out there, wondered, are there other worlds? Is there life on other worlds? And here's just sort of one of the philosophers out of many who wondered about this question. And he sort of assumed, Lucretius, about 2,000 years ago, that nothing in the universe is unique and alone. And therefore, in other regions, there must be other Earths inhabited by different tribes of men and breeds of beast. And so, you know, this is really, I think, kind of even prefiguring the ideas of Copernicus that, like, you know, we're kind of average. We're in an average part of the universe, perhaps. But this is just at this point a hypothesis, an idea about, you know, maybe there, or he's asserting that there might be other Earths out there. And then 1,500 years later, Nicholas of Cusa said life as it exists on Earth in the form of men, animals, and plants is to be found, let us suppose, in the solar and stellar regions. Rather than think that so many stars and parts of the heavens are uninhabited and that this Earth of ours alone is peopled, we will suppose that in every region there are inhabitants. But this was just supposition, and you know, people have dreamed up all kinds of crazy things. Some of them deliberate conspiracy theories. This was the New York Sun, I think, was the newspaper, the Great Moon Hoax. Great Moon Hoax in it was 1835, alleging that Sir John Herschel in his observatory at the Cape of Good Hope had apparently got sufficient resolution with his telescope to see the moon bats flying around. And this is pictured in this engraving. You know, more recently, there's other conspiracy theorists going around. The pyramids were not built by aliens, despite apparently what Elon Musk has been promoting. You know, I'm not sure necessarily he's the sort of best source for you know, fact-based enthusiasts. And people sort of tend to think really that you know, if we are going to go and look for alien life, that maybe you know, we should sort of tune in this kind of way. And there's certainly a lot of kind of conspiracy theories out there on the internet and even on sort of the History Channel and other places that are sort of trying to tell you that, you know, we know what the aliens are doing. There's some sort of conspiracy theory, and you know, the government is hiding the truth from you. But the reality that we've learned, particularly sort of in the last kind of 40 years, basically, is that of the, you know, few hundred billion stars in our galaxy, there may be tens of billions of planets, like small rocky planets where liquid water could potentially exist on the surface. And we now know through missions like the Kepler mission that has measured essentially the sizes and the orbits of stars going around planets going around other stars, and can determine their positions relative to that star's habitable zone. So this green zone shown here, if you look in the central image, I guess if we have a pointer here that I can point at. So in the middle here, this green zone is essentially showing the region where liquid water could exist on the surface of a planet in our own solar system. Venus being towards the inner edge of the habitable zone, but it has a runaway greenhouse effect, so probably not very habitable at the surface, certainly today. Mars towards the outer edge, lost most of its atmosphere over its history, and so, also potentially not habitable today, although tantalizing signs that liquid water has flown on the Martian surface in the recent past, tantalizing signs that there are organic materials there, at least sort of some of the building blocks that one might need for life. And so, there's a lot of focus with missions. NASA has rovers driving around on Mars right now that are scooping up the dirt and sniffing it and trying to see if it can find signs of life there on Mars. And Earth sort of in a nice position here in the middle of the habitable zone, or the so-called Goldilocks zone, where it's not too hot and not too cold. It's just right, again, for liquid water to exist on the surface. And we now know of a number of planets, none of them quite as small as Earth. This Kepler-22b here is a super-Earth, so a rocky planet that is several times the size of the Earth, but it's within its star's habitable zone. And so, we just learned this essentially, in my lifetime, which is, beginning to sort of motivate these searches for life even more. And this doesn't even consider the moons of the giant planets in our own solar system. There's evidence that there's liquid oceans beneath the ice surfaces of some of these moons, and proposed missions to go and fly through the plumes on Enceladus, for example, and try and sample them to see if there's organic material there, or even signs that life exists there in the present day. So you don't just have to restrict yourself to the habitable zone. And if you think about the universe as a whole, so this is the Hubble Ultra Deep Field. It's 11 days of shutter open, basically pointing at this grain of sand size region of the sky as held at arm's length on the sky. And the star in the middle here is about 20,000 times too faint to be seen with your unaided eye. And that's one of the brightest things in the image. And so essentially what you're looking at here, again, is a grain of sand held at arm's length, which would appear completely blank if you were to go out and stand on the roof tonight and figure out where this location was in the Hubble Ultra Deep Field. And Hubble stared at it for 11 days, and it saw about 10,000 galaxies. So pretty much everything in this image here is galaxy, 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 galaxy. All these little dots that you maybe thought were stars. The stars are the bright things with or mostly the bright things with these diffraction spikes on here, but most of the stuff in the background here is galaxies. So galaxies, as far as the telescope can see, and then by extension, and this is just within our own observable universe, right? Maybe 1 trillion galaxies, each potentially containing hundreds of billions of stars. So there's a lot of real estate out there. And if you think that, a large fraction of those potentially are habitable zone planets, then, maybe you have to ask yourself, as Enrico Fermi famously did, where is everybody? This is known as Fermi's paradox. It's not really a paradox, and probably Fermi wasn't the first one to wonder this, but, if there's all this real estate out there, if there are the ingredients for life and the conditions for life, then why have we not seen evidence for life? The pyramids and the tinfoil hats notwithstanding. Might need my glasses for this one. I don't know how good you are at reading cursive, but this is a letter from Nikola Tesla in 1937. And he says, undoubtedly, there are myriads of planets in the universe which were, are, or will be abodes of life in its highest forms. The same formative principles must be operative. Again, this is the Copernican principle, basically. In the building up of the bodies of the inhabitants, and their perceptions of an external world must be closely similar to ours. It is highly probable that many are as far or even more advanced than ourselves. Codes for communication and mutual understanding can be readily formulated on the basis of commonly perceived universal truths. And then he says, by my inventions, I guess he was not a particularly modest man, it has become possible to transmit considerable amounts of energy at distances of thousands of light years. And if received, it can be easily detected in many ways. So this was back in 1937, and Tesla's already talking about interstellar communications as a way that potentially we could look for other life out there, right? So this is really sort of setting the groundwork for what became known as SETI, the search for extraterrestrial intelligence. Or alternatively, in sort of modern usage, we've been using the term technosignatures. which are indicators of technology as a proxy for intelligence that might have created them. And this is sort of by analogy with biosignatures. I'll talk about this a little bit more later in the talk. But there's a lot of focus on looking for signs of biology in exoplanet atmospheres, for example, these biosignature searches. And what Tesla's proposing here is, well, you know, we could detect technology, even Earth-like technology, the kinds of inventions that we had in the early 20th century, under some optimistic kind of back of the envelope calculations at distances of thousands of light years. So that's pretty impressive. It took another sort of, I guess, 23 years for the first actual search to be done. Frank Drake was employee number 4 at the Green Bank Observatory when it opened in the late 1950s. And he did his first search using the Tatel telescope here, an 85-foot telescope at the Green Bank Observatory in 1960. And he used this instrument here, you can see on the right. The instrument was actually designed for surveying hydrogen gas in the galaxy. And so it was tuned to a frequency of 1420 megahertz, a wavelength of 21 centimeters. If you're familiar with the 21 centimeter line from hydrogen, traces gas in the galaxy. And it's been sort of hypothesized that this would actually be a good frequency to search for if you're looking for transmissions from an extraterrestrial civilization, because if we're studying hydrogen in the galaxy, then they might also be interested in mapping hydrogen in the galaxy, and they might try and get our attention sort of thinking of the idea that, okay, if somebody's looking at doing a hydrogen search and some sort of obviously artificial signal shows up in that band, then that's a good place to look when you don't know what frequency you should be tuned to in the first place. And so this is an example of what's called a Schelling point from Thomas Schelling, a game theorist who proposed this idea that, essentially if in the modern parlance, if you or I are in New York City and our cell phone batteries are dead, where are we going to meet up? If we're trying to get together, we're probably not going to go to, 57th and Lexington at 2 o'clock in the morning. Probably a better plan will be to go and stand underneath the clock of Grand Central Station at noon, right? And if you think that's a good idea, and I think that's a good idea, then we're more likely to meet there at that Schelling point. And similarly, 1420 megahertz could be a Schelling point in the sense that if we know ahead of time that any radio astronomer will be interested in looking at this frequency, then transmitting at that frequency to get somebody's attention might be a good strategy, aside from the fact that you'll be interfering with your fellow radio astronomers' 1420 megahertz observations, which they might get a little annoyed about. Now, as it happens, Frank didn't pick that frequency because of any of those philosophical considerations. He picked it because there was a receiver there that was surveying the galaxy at 1420 megahertz, and he was just borrowing time on this instrument. And really, this has been sort of also a thread in the history of SETI research over intervening years. For a large fraction of the time, we've been sort of begging and borrowing time on other people's telescopes and other people's instruments. But there's still quite a lot of searching that's been done over that time. Another sort of pioneering realization that Frank came up with, just sort of sketched on a whiteboard at the Green Bank Observatory at a meeting in 1961, where there were a number of luminaries, including one of the attendees who learned that he'd won the Nobel Prize in chemistry while he was there, and also a young Carl Sagan was at this meeting. And they sketched out this equation, Drake equation, on the board, and this essentially sort of parameterizes our ignorance about the prevalence of life in the galaxy. And so you have this number n on the left side of the equation here, which is the number of communicating civilizations right now in the galaxy. And in order to figure out what that number is, we need to know our star, which is how many stars per year are being formed in the galaxy. We need to know what fraction of those stars have planets. We need to know the number of planets per star that are Earth-like. So these are potentially habitable zone planets. The fraction of them that have life. The fraction of planets with life that develop intelligence. The fraction of planets with intelligence that develop the ability to communicate. And then the lifetime in years of that communicating civilization. The reason why this is a lifetime in years is because this is a star formation rate in stars per year, and so those cancel out, and you end up just with a number, and it's the number of communicating civilizations in the galaxy right now. We'll get back into this a little bit later. I'm not going to kind of get deep into equations in this talk, but this is sort of an important one in the history of SETI. So just to go through it again, right, the number of communicating civilizations is the rate we're forming stars, the fraction of stars with planets, the number of habitable zone planets per star with planets, fraction of them with life, fraction of those with intelligence, the fraction of those with communication, and the lifetime of that communication technology. And so, you might think of this as the lifetime of the civilization itself, or you could think of it as the lifetime of the communication technology. So some of you may well ask me in the Q&A, well, what if they're not using radio waves, Steve? Well, then L is, maybe 100 years or 200 years, so the number is going to go down. If they move on to something else and we're doing a radio survey, we're not going to find that. So Drake's N in this equation is the number of communicating civilizations out there in our galaxy that you could essentially hope to make contact with, assuming that they have sufficient power to transmit to you at the present time. And again, we can sort of dig back into that a little bit later. So we know that number is sort of roughly 5. There's roughly 5 stars per year formed in the galaxy, give or take. And that was the only number that Frank knew in 1961. But as I said earlier in the talk, we now know that pretty much every star has planets. And maybe 1/5, well, maybe not 1/5 of the stars, but an average of 1 in 5 habitable zone planets per star that has planets, basically. And so you multiply those numbers together, and certainly the way that I've constructed this here, you can see those numbers just multiply to 1, which is kind of convenient. But then we don't know the fraction of planets with life. We only have one example here on Earth. We don't know the fraction of planets with life that develop intelligence. We have one example here on Earth, and we don't know the fraction of those that develop communication. We only have one example. But if you're an optimist about these 3 numbers, and you said, well, the Copernican principle, right, the chances that life arises, I think it must be pretty common. I'm going to set that number equal to 1, and I'm an optimist about intelligence, and I'm an optimist about communication, then you'll see you just have n equals 5 times 1 times 1/5 times 1 times 1 times 1 times L, or n equals L. Maybe you're a pessimist about L because you think the killer robots are going to take over, if you've been reading the news recently, or some other apocalypse might be coming. And why does that go back to that? I'm not sure. Okay, this is illustrating the point that I was making. 1, 1, 1. And that was actually Frank Drake's license plate, n equals L. So Frank was an optimist about this. But essentially, we can go out and measure these things, and NASA's trying to measure the fraction of planets with life directly, and we're trying to just sort of measure everything and kind of fold it into this n. If you like sort of funny license plates, mine incidentally is 1420 megahertz. I was kind of surprised that was available still in California. I was pretty psyched to get that on the truck. If you see me driving around town, give me a wave. And really sort of that was again sort of borrowing time on other people's telescopes was kind of the thing, with some notable exceptions, until in 2015 the Breakthrough Listen project was announced. And so this is it was a pledge of $100 million over 10 years. It's actually recently been extended to certainly until the end of this decade. Private philanthropy through the Breakthrough initiatives to revitalize the search, to pay for time on telescopes in some cases, to pay for equipment, and to pay for people basically to do the search. And so we're back at Green Bank again. I'm responsible for our program, as you heard in the bio, on the Green Bank telescope, the world's largest steerable single-dish radio telescope, 100 meters in diameter. To give you an idea of the scale here, these guys had just rappelled down from painting the underside of the dish when I took this picture. It's our chief engineer, Dave McMahon, who built the back-end instruments, and these are regular-sized vehicles. That's not my truck, but it is a regular-sized truck. So this thing is huge. And we're using this substantial fraction of the time on the GBT to do the search. So if you're trying to do a SETI search, Frank had one single channel with his instrument, so essentially sort of tuning into one radio station and tuning that across the radio dial, and he looked at 2 stars. And the second star that he looked at, actually, he thought that he detected a signal. He had detected a signal, but then they realized when they hung a smaller antenna out of the window of the control room and saw the same signal, that the signal wasn't coming from the sky, right? So you're comparing the signal from the telescope with a comparison signal and determining, okay, this is local interference, and actually probably a high altitude aircraft in the example of Frank's first search in Project Ozma. So where are we now? Well, we have, the Moore's law sort of increase in computing power. We have these modern computer systems, and this is just one computer server in the rack that we have, or several racks of computers that we have out at Green Bank here. And on the right here, you see the data that we get when we point at a star using the telescope. And I'm going to show you a few of these so-called waterfall plots, or dynamic spectra is another word that's used here. And what you're seeing here is on the horizontal axis here, you're seeing frequency. And so, I already talked about frequencies at 1420 megahertz. Here we're up at 2400 megahertz. And then you're seeing time in seconds here. So this is 5 minutes of time on the vertical axis. And then the colors here are showing you the intensity of the signal. And so, what am I seeing here? I'm seeing how bright the radio waves are coming in as a function of frequency and as a function of time. And ignore these this little sort of grid that's basically an artifact of the way that we split up the frequencies here. But these squiggles that you're seeing here are real signals that are coming in. And so, you might say, again, like Frank did, well, can it be this easy? Can we find alien transmissions by just looking at plots like this? Well, you might be able to see some sort of faint lines here at 2400 megahertz. And if you've looked at your Wi-Fi router at home recently, you might realize that that operates at frequencies of 2.4 and 5 gigahertz, or 2400 and 5000 megahertz. And so this is probably Wi-Fi. This is probably either somebody who's ignored the signs of the telescope saying, please turn off your cell phone, or one of the locals that really, is maybe not too happy about living in the middle of a national radio quiet zone near the Greenwich telescope and decided, I'm just going to get a Wi-Fi router and get online that way. We have now, the ability to detect a much wider range of frequencies, but again, we have so much radio frequency interference, or RFI, in the present day that the challenge has gotten a lot more difficult than it was back in the early 1960s. So here's a fallback end. I showed you one of those servers, and that output was 187.5 megahertz wide chunk of the band. We can now get 12 gigahertz of the band from the GBT with 3 hertz resolution. And so essentially this is billions of channels. Frank had one channel, we have billions of them that we can tune to at once. And we have a ton of storage. So this is sort of 8,000 of your average laptops. And we've been observing 5 hours a day with the GBT. And if you're wondering why those numbers don't add up, it's because we cannot save all the data. We have to sort of do some triage and some analysis of the data, and then we archive a sort of much reduced data product. But it's a real challenge and an opportunity with all of the data that we get out of telescopes like this. So I mentioned this already, we're in the National Radio Quiet Zone, so a federally mandated large area where essentially the FCC controls a lot of the transmitters that can be in place in that zone. But you still have people with their phones not switched off. You have planes going overhead like Frank did, maybe not so much garage door openers, but maybe some Wi-Fi. Increasingly, satellite constellations like Starlink. Sorry, I'm gonna rag on Elon Musk again. It is good to be able to get internet, if you're in the middle of the ocean or something, but Starlink is also not great for radio astronomy. Microwave ovens, I'll tell you a story about another telescope in Australia that had some issues with confusing microwave ovens for real signals from the sky. So this is, a real thing with sort of astronomical observations of all kinds, so they can be interfered with by this RFI. And here's a table that the Federal Communications Commission, puts out. You can find this on Wikipedia, starting at frequencies of 3 kilohertz up in the top left and going down to 300 gigahertz in the bottom right. And they very helpfully reserve some frequencies for radio astronomy. Here's on 1420 megahertz. Here are radio astronomers. You can have the 1420 megahertz band, but as I just explained, we're now straying way outside of our lane in terms of the fact that we're ingesting 12 gigahertz across this band. We're picking up the mobile satellite communications. We're picking up, navigation satellites. There's all kinds of things that are transmitting. And again, this isn't just a problem for SETI searches. It's a problem for radio astronomy more broadly. Even out of those bands, so the Starlink satellites are supposed to be transmitting at about 11 gigahertz, but there were some observations done with a LOFAR telescope at frequencies of only around 100 megahertz, where LOFAR actually picks up the electronics on board these satellites that are not adequately shielded. And so even those little sort of chunks of the spectrum where you think the FCC is saying this is your lane, stay in it, there's also interference that's coming from outside of that. It's a real haystack of interference, particularly in our modern electronic age. And so this is a real challenge. And it does become a needle in a haystack problem. If you have a signal that you're interested in, the haystack is only getting bigger. And in the sense of a SETI search, we don't even know if there is a needle in the haystack. And if there is one, we don't know what kind of needle it is. Is it a sewing needle or a knitting needle or a Seattle space needle, right? We really kind of, don't have a good kind of conception of, what might be in the data. And so we need sort of smart techniques to try and pull out things that look interesting. So how do you search for interesting signals? Well, If you're familiar with the directional microphone, you could pick out one person from a crowd if there's a crowded room where a lot of people are talking by pointing the microphone at them and then pointing the microphone in another position, pointing it back at the person that you're interested in, and doing this comparison on-off when you're pointed at your target and away from your target, and seeing does the signal come and go when I'm moving on and off the person that I'm trying to pick up. And so we can do a similar thing with the GBT. So it has what's called a primary beam, which is just the region of the sky that it's sensitive to. It's actually several times bigger than the Hubble Ultra Deep Field that I showed you earlier. And so we're actually getting not just the stars in the foreground that were pointed at, but we're getting all of those galaxies in the background as well, which is kind of a cool way of sort of improving the figures of merit for our searches. But with an instrument like this, essentially, you're looking at still at a fairly small region on the sky, not sort of grain of sand size, a few times that size. But then you can target a particular star and compare the signals that you're getting when you're looking at the star and when you're looking at a neighboring position. And that's exactly what we do. You'll see in this animation there's some cool planetarium software, by the way, called Stellarium. You can get a free version on your laptop or on the web. There's a free version on your phone. You can also pay a couple of dollars to unlock all the features on that. Definitely recommend that planetarium software. And I've used it here to just kind of illustrate the kind of observing technique that if we were looking at the star Vega here, you'd spend 5 minutes looking at that star, 5 minutes at a neighboring star, and then 5 minutes back on the primary target, 5 minutes at another neighboring star, 5 minutes back on the primary target again, and 5 minutes away. And so this is what we call a cadence. It's 6 5-minute observations. We're now going to zoom across the sky to a different star here. And you can see in this part of the sky, there's all of these satellites. I mean, you see these satellites in low Earth orbit here that are whizzing by. If you're out, probably tonight, shortly after sunset, you'll see some satellites in reflected sunlight. But these are their positions. Many of these active satellites that are transmitting radio waves, and also the ones here that are in the so-called geosync belt. And so these are ones that don't change position on the sky, which is why your direct TV dish is always pointed in one direction. So they're in an orbit where their apparent position doesn't change. But the nice thing that you can see if I run this again is that these on-off comparison observations actually enable us to filter out, even when a satellite like that passes very close to our target position, it should still enable us to filter out signals because it's unlikely that we're going to hit a satellite on 3 successive on-scans and then not hit the satellite on those 3 successive off-scans. And so comparing these on-off signals in this cadence can enable us to apply essentially a spatial filter and try and isolate things that are just coming from this one position on the sky. So a sort of updated version of Frank hanging the second antenna out of the window back in 1960 for Project Osmo. Another technique that we can use is probably if you've been to Astronomy before, you've heard something about redshift. So this Doppler shift that you're familiar with, don't stand in the street in front of an ambulance to test this out. Although I guess if you are going to stand in the street, then maybe do it in front of an ambulance, because then they'll just load you in the back. You can hear the pitch of the ambulance siren shifted from its rest frequency as it's in motion towards you. So if it's coming directly towards you, it's going to be blue shifted. It's going to go towards higher frequencies. If the ambulance is moving away from you, it's going to be red shifted and go to lower frequencies. And we see this with light, with galaxies. Now we know the universe is expanding. What we don't see as often, and what you won't hear about as much in astronomy talks, is this is a Doppler shift, but we're relying on a Doppler drift, which is a change in that frequency, which is akin to an ambulance going past you on the street. And so the relative velocity is changing, and that's why you hear the change in pitch over time, right? And that Doppler drift, that change in frequency over time, is an indication that something is accelerating with respect to the velocity is changing. And how can we use that as a filter? Well, we have telescopes like Green Bank and Parkes that are on a rotating planet. Our planet is rotating around the sun. A transmitter on a hypothetical exoplanet, which is also rotating, is also going around its star. And so there's going to be some relative motions here. There's going to be some accelerations, which are going to lead to a Doppler drift, a change in frequency over time. And so we can use that to pick out signals in a cadence like this. So again, these are frequency on the horizontal axis, time on the vertical axis. And now I've stacked 6 of these scans. So 6 scans from the cadence here, right? So we're on target. Actually, I have illustration here, on target, off, on, off, on, off. And you can see the signals of the red dash line in the middle here is just there to guide your eye. You can see the sort of yellow and green signal, so there's more power coming in this narrowband signal, so a narrow range of frequencies. That's an indicator that this is artificial. Nature doesn't make signals that are that narrow in frequency. And there it is drifting. So there's an indication that perhaps it's in motion relative to the telescope. This is not somebody standing there with their cell phone nearby. It's not sort of a static interferer nearby. But if you're paying attention, you'll see it's in both the on and off observations. And so it's failed the spatial filter. It's not isolated on the sky. When we move the telescope on and off the target, the signal is still there. And so we don't sort of keep this as a good candidate SETI signal. But here's a good candidate SETI signal. Again, ignore the red dashed line. That's just there to guide your eye. We've got a drifting signal. So it has this Doppler drift that we're after. It doesn't appear to be local. It's there when we look at the primary target. It's gone when we look at the off target, and then we reacquire it again, and then it's gone, and it's back, and it's gone. And I would like to present to you, ladies and gentlemen, this evening, a detection of extraterrestrial intelligence made by a high school teacher working with me a couple of summers ago. It's extraterrestrial and it's engineered, but it's our own engineering. It's Voyager 1. We sent this ourselves into the outer solar system. It's 20 billion kilometers from Earth. It has a 23-watt transmitter on it, so about the same power as the light in your refrigerator. It's hooked up to a 3.7 meter antenna, which is pointed back at Earth, picked up by the 100 meter Greenbank telescope. And essentially that 3.7 meter antenna makes it look like a 1.3 megawatt transmitter, even though it's 20 billion kilometers away. And so we can pick it up loud and clear with our telescope. And now we just have to do that 10,000 times further away for the nearest stars, which is hard, but not impossible. Now, again, you could do the back of the envelope calculation. Tesla kind of did this, and he's like, well, if they had a bigger dish, if they had a 100-meter dish at their end, then you actually could do this at distances of thousands of light years with no technology more advanced than what we have in the present day. And of course, there's no reason to kind of limit ourselves to what we have in the present day, right? Technology keeps on mounting onwards. If any of you like playing around with Python and downloading data, there's a little link there. I can also pop it up again at the end if anyone wants. So what else can we do rather than physically moving a 7,000-ton dish in West Virginia in order to filter out those images that are coming from the sky? And what could we do maybe that doesn't require us to go and buy time on a telescope, but to go back to sort of Frank's technique of borrowing somebody else's time? Well, we can use telescope arrays like the Meerkat array in South Africa, commissioned now and observing for about the last 5 years. And we have now more of these servers that I showed you at Greenbank that are deployed out in South Africa at the data center for Meerkat. And what these can do essentially is combine the signals from these telescopes. So these telescopes are smaller, which actually means they see a larger area of the sky. And within that large region of the sky, there are many potential targets that we might be interested in as SETI targets. And so we can use a technique called beamforming, which combines the signals from those telescopes. So within that primary field of view there from each of these dishes, you can then synthesize all of these telescopes together and combine the signals up in order to steer these individual beams that point at the targets that you're interested in. And now we don't have to move anything. We can compare the signals between the beams that are pointed at the target that we're interested in and those that are pointed elsewhere, and see if the signal really, does it appear to be coming from the sky? And again, this just takes a lot of computing hardware. But the nice thing is that we can do this at the same time as somebody else is using the telescope. And so here's your primary user of the food bowl here. And this is a commensal user. And so commensal just means eating from the same table. The dog here is a commensal user of the dish. And he's actually not even eating the food here, he's just looking at it. And so if he could do a little bit of beamforming, then he could sort of look at the targets that he's interested in. The primary user doesn't even know. I mean, this primary user does seem a little bit oblivious to the fact that the dog probably is interested in eating the food. But essentially, just by deploying some computing hardware and by plugging it into a big fat Ethernet switch at these sites, we can do our science while the primary user is doing their science as well. And so that's a win-win. So I won't sort of go into detail about the hardware that we have out there. But again, at Greenbank, we have 64 of these compute nodes. We have 105 of them out at Greenbank, a whole ton of storage. And this is now running in parallel with the main observations taking place there. And this is going to enable us sort of over the course of, a relatively short period of time, and this has already begun. So we're already looking at hundreds of thousands of stars with less sensitivity than we get with Greenbank, in part because many of these stars are further away. There's the plot of that on the left there. but it's enabling us to cast a really wide net of observations for the stars that are being surveyed by Meerkat for other reasons. And then if any of you have seen the movie Contact, Jodie Foster sitting on the hood of the car with the headphones on at the Very Large Array, we are now finally doing SETI at the VLA. That wasn't taking place until relatively recently. So COSMIC, this is one of these sort of contorted astronomical acronyms, the Commensal, you know what that means now. Open source multi-mode interferometer cluster. You can tell they came up with the acronym first and then sort of shoehorn the name of the instrument into there. And so this similarly is operating in parallel with the primary observations, 24 nodes out there, and that can only handle 1.4 gigahertz of bandwidth. We get 12 gigahertz of green, but the signal's coming in from all 27 antennas of the VLA, and this has been written up in some papers in the literature if folks want to go and they can follow it up. And then eventually, these arrays are going to form the basis of the next generation radio telescopes, the square kilometer array. So here's at the Meerkat site in South Africa, the square kilometer array mid-frequency array is going to be built out. And in Western Australia, there's going to be a low frequency component of this. And construction has already begun on this. And the director of the SKA has listed SETI as a critical component of the future science case. But what if we miss a signal? Some of this haystack before here in this cartoon, the professor makes the horrifying discovery that messages sent across the universe by advanced alien civilizations in unknown solar systems have all been going into junk mail. So, you can be sort of overzealous and throw things out that you're interested in, or you can just be sort of not very good at finding the interesting things in the data set. And, there's this analogy that some of you, if you've heard talks about SETI before, will have heard this analogy of a glass of water in the ocean. This is at least popularized, if not originally, due to Jill Tarter, one of the pioneers in SETI. And Jill said if you went and scooped a glass of water out of the ocean and held it up and looked for fish in the glass and didn't see any fish, you would be foolish to conclude that there were no fish in the whole ocean, right? It's now somebody did a back of the envelope calculation and figured out the amount of searching that we've done now is more like a hot tub's worth of ocean compared to all of the oceans in the world. So we've surveyed more of the parameter space, but it's still not very much of the space that we've searched. But I would make the argument that, rather than just staring at the glass and saying, okay, I'm done looking for life in this glass, if you use some different techniques and put it under a microscope, you'll see that it's teeming with life, right? I'm not saying that's necessarily the case for the kinds of observations that we're doing, but it does suggest that maybe using different techniques to look in this haystack, if I'm mixing metaphors here, haystacks and oceans, but to look at that search space and to find things that look interesting. If we can come up with techniques to do that, then maybe we'll find the kinds of things that we're looking for. Google's already figured out how to do this. You get a Google image search, you type in ET, and Google will give you many examples of ET, although you'll notice there's a certain similarity between all the examples of ET that it finds. And then if you go to Midjourney and you plug this into a generative art algorithm, which I know a lot of you have been playing around with in the last year or so, and say, show me ET, it's like, yeah, ET is a kind of lizard-like thing that rides a bicycle because it's ingested all of the other stuff with a sort of labeled training data right from the internet, and it's trained its algorithm to say, I'm now going to reproduce this. And this should also worry you all, if you take nothing else home about, SETI or about radio astronomy tonight, this should worry you about bias that's built into AI systems, and we really have to be aware of that, right? If these things are making, your car loan decisions, if there's some AI algorithm that somebody hasn't worked to kind of to check for bias, then it can be baking in existing biases and making them worse. And I think, it's also sort of incumbent on us who are using these tools in science to realize there are limitations to them. And some of those limitations may be kind of quite sort of subtle in the sense that it's only kind of a subset of the overall sort of range of possibilities that could be out there. And so, with that caveat, we have been playing around quite a lot with machine learning. So Brian Brisky, who's finishing up his PhD here in Berkeley, came up with an algorithm that injects these sort of artificial narrowband signals into data. And so, we don't have a lot of examples of extraterrestrial transmitters, right? When we have the Voyager 1 probe, we have a few other sort of interplanetary probes, but we don't have any real alien signals to train on. So we have to simulate them, again, with the knowledge that this may be some limited subset of the possible range of signals that's out there. And then once we've injected them, then we can train algorithms that will then go and find them. And Brian was able to show that he could do a better job recovering these signals in noisy regions in the presence of RFI than we can do with our standard pipeline, which you'll recall was also good enough to find Voyager 1, right? I don't think I sort of completed the story there, but the high school teacher that was working with me came and said, I found, I knew we were pointed at Voyager 1, right? I gave him the data set, and he came back and he said, I found this signal, and the signal was Voyager 1. So the algorithm works, but we want it to work in noisier environments in the presence of more RFI, because as I mentioned, that's only getting worse. Another student, this is Peter Ma, he started working with us when he was a high school student, actually, and he's going to be coming in the new class of graduate students coming in here in Berkeley in the fall. So we're glad that Peter's joining the group here in the astronomy department. And Peter was also working on algorithms here where, you can see in the two examples here, this is simulated data. You're all hands with these cadences by now, and you can all obviously spot that the one on the left is not a good SETI signal because it's in the ons and the offs. The one on the right is a good SETI candidate because it's only in the on scans. Even in the presence of all of this, as background scruff here, this other sort of radio frequency interference. And so Peter used a technique called an autoencoder. And so there's a sort of pictorial example of this here, where essentially you train an algorithm. This is sort of in a cartoon example to generate numbers. So you're feeding a number 4 in here. The encoder sort of boils this down into some sort of compressed representation, what we call a latent space here. And then a decoder works to turn that back into a number 4. And maybe you're thinking, if you haven't seen these before, well, that's not very impressive that you can take a number 4, put it in an input, and then you get a number 4 out. I mean, great. What does that tell you? Well, it tells you that this compressed representation is an accurate representation of the thing that you fed in. And so now what we can do, if you also train this for numbers 5 and 6 and 9 and so on, then by comparing the representations in this latent space, you can say, oh, I'm pretty sure this other handwritten numeral is also a number 4 because it clusters in this latent space with the other number 4s. And then this group of things over here, they might be 9s, and these might be 0s. And so Peter's done something akin to this with this training data, training this autoencoder to recognize, okay, these signals are similar to each other without actually really kind of having to specify in which ways they are similar, just by feeding them in and asking the machine to learn these representations. Then he's able to then go and deploy that on real data, and he's able to find things that look pretty interesting. And these are real signals that have been missed by the existing pipeline. We've also now tuned up the existing pipeline, so it's doing a better job of pulling out signals like this. But this made a little bit of this was my interview in space.com, made a little bit of a splash in the media. I think they kind of liked artificial intelligence looking for extraterrestrial intelligence is kind of a good sort of tagline for this. But running on these large data sets, right, finding interesting things, there's a lot of potential here for ML. We also had we have a summer internship program here. If any of you are current undergrads or no current undergrads or will soon be undergrads, consider applying for our summer internship program. So we take about 8 or 10 students a year here in Berkeley. And one of our summer students, Sophia Sheikh from 2016, is now a postdoc over at the SETI Institute. One of our summer interns from 2020, Shane Smith, is now an engineer at Aerospace Corporation. And Shane spotted some interesting signals in data from Parkes, went and alerted Sophia and the rest of the team, and we kind of dug into this, and we thought, well, this is interesting enough. This sort of passes the threshold enough that we sort of started talking about this as a potential candidate. And indeed, it was sort of labeled Breakthrough Listen Candidate 1. This leaked out somehow. I don't really know how. Initially to The Guardian, then the New York Times got hold of it, Scientific American. There's a lot of excitement. This was a good dry run for us as well, right? Because it's like, okay, the media didn't go completely nuts. That's sort of reassuring. And this is just a little snippet. So, the on observations here, the off observations here. So these were not, for various reasons, equal in length and time. But the signal looked pretty good. And so we then had to go through this whole vetting process. And eventually we decided this is not aliens, we're going to throw it out. But it involved, this complicated flowchart that we came up with. Not going to take you all the way through this. But, number one, is your instrument working? I mean, it's always good to check in the first place. There's a signal only out on source. Well, that's a good check to have. Is there known RFI at that frequency? Is the drift consistent with human technology, with expectations? There are similar signals in archival data, right? So you work through this, and then you're still pretty skeptical, right? We're not really going around, waving our hands. We found the aliens. We found the aliens, right? We got to kind of search through this and be pretty skeptical. And then if it does survive this, then okay, we got to go and observe it with other facilities, and that's really the good check there. And so, here's ET again. And this sort of is going to help us, basically do sort of some of the last set of checks in here, which is, do we see similar signals in other observations? And Google will also let you do a reverse image search where, you put in ET, and then without telling it, I want ET, you just like find me more things like this. And again, it's using this sort of clustering in some latent space to say, well, here's some other stuff that you like. I don't know why this is 49 pounds and 41 pence, but anyway. That's how much ET costs these days, apparently. So you can do this reverse image search. Peter also had a nice little paper. I suggested to him at a meeting just before the holidays a couple of years back, and I said, I think we could just kind of deploy this as a reverse image search. So we're not sort of doing this forward. We're now putting in an input image and saying, can we find things like this? And we came back after the holiday break, and I had a Zoom meeting with Peter, and he's like, so I built that thing you mentioned before the holidays. I'm like, oh, okay, cool. Let's see how this works. And he put in, a signal over here, and then it's like, okay, I found a match. The best match is actually the input signal, so that's good. That shows that this is working. And then it finds a bunch of other matches as well. So this is a good way to kind of vet, is this signal truly anomalous, or is it one that we see in the data all the time? And this might also help us kind of chase down, if there is some interfering signal at the telescope, for example, that's coming from some electronics, then maybe we could go and shield that or turn it off or something. And so this sort of tool can be used kind of more broadly, potentially in radio astronomy as well. Okay, I'm going to shift gears a little bit here because I've been talking about radio astronomy a lot, and I'm going to talk about optical astronomy. So probably many of you have seen an animation like this of the transit method of finding planets. And so this is sort of one of the primary tools for finding planets around other stars. I mentioned the Kepler spacecraft earlier, which uses this technique, the TESS spacecraft as well. And so you're watching, you see in the plot down here, this is the intensity of the light as a function of time. We're zooming around into the plane of the orbit of the planet here. And you see as the planet passes in front of the star, the light dips down. And then as it finishes crossing the star, the light comes back up to the original level. So it's just the disk of the planet blocking out light from the star. And by the distance between those transits, the so-called transits, and by the depth of the transits, you can tell the planet's orbit and the planet's angular size relative to the star as a whole. And so this, has been, again, sort of a workhorse technique for finding exoplanets. But, what if we imagine some sort of advanced civilization that is playing around with engineering things like this? This is an artist's impression of a Dyson structure, sometimes referred to as a Dyson sphere. You can also mention Dyson swarms, so structures that are in orbit, maybe collecting energy from the star, maybe for extra living space, if they run out of space on the planet. And, far-fetched, right? But, if you think, again, back to the Drake equation, n equals L, the interesting thing with that is that if n is large, then it might be because L is large, right? Certainly, if you're an optimist about those F fractions, right? If you just go to n equals L, like on Frank's license plate, if L is big, then n is necessarily big, okay? So that means there's lots of them to find. And so if we do a survey and it's easy to find things, then it's because L is big. And if L is big, that means they're potentially very advanced, right? Because, if L is 100 years, if the communicating civilization lasts for 100 years, there's only 100 of them in the galaxy. If L is 1,000,000 years, then you find them and they might be hundreds of thousands of years more advanced than we are. And so, that's one reason why it's not sort of too crazy to think about kind of wild extrapolations from current human technology. And at least to imagine extrapolations to the point where we could go out and do an experiment to find, is there anything like this? So some of you may have heard about Voyager star back in 2015. A lot of excitement about this particular object, which is a star that's behaving really quite strangely. And so here's one of those light curves. So if it was a planet, you'd expect a little dip, and then another little dip, and so these regular dips. So what you see actually is irregular dips, and some of them that are so deep that the 20% of the light of the star is blocked down. So like this is weird, like this doesn't really make a lot of sense, particularly with this kind of irregular aspect of this. And so there's been a lot of attempt. I mean, initially, sort of some people saying, could it be, a Dyson structure that's in construction around the star? I mean, again, aliens should never be your first explanation. If somebody is running to aliens as an explanation for an astronomical phenomena, and some of our colleagues sort of have more of a tendency to do that than others, then be a little bit skeptical. But, it is interesting nonetheless, right? Voyager star is interesting. And so we had an intern a few years back called Piper, and she used some software to actually, we were playing around with kind of different shapes passing in front of stars, and she thought it'd be fun to kind of put her name in planet-sized letters. We don't really think the aliens are using the Roman alphabet and building sort of planet-sized letters like this, but you know, that's what this would look like if you flew these planet-sized letters in front of a star. It's kind of cool. And she did this with all the other interns names as well. It's a little kind of side project. So, you know, you can simulate things, you can inject signals into the data, and then you can see, well, what kind of signals can we retrieve using the algorithms that we have, and essentially sort of put some constraints on the presence of things. And this is some work in progress from John Huang here, another colleague, where, you know, he's put some input shapes in here, seen what they do with a light curve, and then trained this ML algorithm to recover, to try and reconstruct the shape that goes in. And so, you know, some sort of neat tools here essentially for trying to pull out, you know, other odd things happening in light curves. Another summer intern is now a graduate student at CU Boulder, Hannah Zuckerman, and she did a search using, again, with the Kepler light curves to see, you know, are there any individual transits that are weird shapes? And so again, like Voyager saw there, could you find transits that don't seem to match the other transits, maybe transits that are missing, transits that are offset in their position, in their timing, basically. Again, I mean, no real sort of reason to believe, right, that an advanced civilization would choose to do this. But if you find this, it's interesting, whether it's aliens or whether it's kind of some weird astrophysics, right? And Anna also had a project working with another student, Zoe Ko, to look in high-resolution spectra from the automated planet finder to see, you know, if they're not using radio communications, but potentially laser communications, could we see that laser light, these narrow lines in laser light at interstellar distances? Again, the back of the envelope calculation, it's not that crazy to try this, right? Another technique that you can use, we talked about Schelling points earlier. And so there's this idea called the SETI ellipsoid and variations on it, where you imagine some bright event like a supernova explosion that everyone in the galaxy could see. So everyone will notice when a supernova goes off in our own galaxy. There have only been a handful of them in recorded history. And then you imagine alien civilization over here sees the supernova, and sort of immediately afterwards, they have their system set up and ready to go. They broadcast the signal out that essentially says, I noticed this supernova, right? Or, I mean, you know, maybe it mimics the light of the supernova. Maybe it's some indication that it was that supernova. And then the point is here we are on Earth. Here's the Gaia spacecraft, and it's looking at these stars. And if it were to see a signal that appears coordinated with the original coordinating signal from the supernova, then it's an indication that somebody saw that too. And essentially, there's some sort of back of the envelope math that you can do that shows that this means it traces out an ellipsoid in space, which tells you where to look at a particular point in time, essentially just from geometry. And so there's been a few papers with this sort of searching through existing data sets to see, you know, do we see anything weird happening at these particular times coordinated with historical events like supernova 97A, for example. Haven't found anything yet. You know, as a colleague came up to me at a meeting recently, Australian colleague said, found any aliens yet? And I said, well, no, but we've found none of them in a larger area of space that we've never found. Didn't really seem satisfying. But, you know, it's of interest. You know, the Economist was mentioned, the bio. I think this was a nice one, also kind of featuring a couple of our students who did some work on this university. So that, you know, there's broad interest sort of in the public, as evidenced by the fact that you're spending an hour of your evening here with us. Another thing that's coming along in the near future that you may have heard about in some other talks is the Vera-Rubin Observatory and its legacy survey of space and time, or LSST. This was originally the Large Synoptic Survey Telescope. So again, they like the acronym and sort of made a backronym out of this with LSST, the Legacy Survey of Space and Time. And a student working with us last summer at the University of Oxford was looking at the simulated data that is expected to come out of the Rubin Observatory with a focus on objects in the solar system. And so I'm not going to sort of go into detail on these plots here, but essentially what you have here is distance from the sun, and then various other parameters that parameterize the orbits of these objects in the simulation. And what Brian was able to do here, he's putting up on the left kind of the distribution of these objects in orbital and color space in the solar system. And then he trains an algorithm called the Gaussian mixture model, which you can see on the right here, and just eyeballing this, you can say, okay, this is doing a pretty good job of reproducing what's in the simulation. So we now are pretty confident that, again, like that latent space representation that I showed you earlier from Peter's work, that we have a good representation of the underlying data. And Brian also used a similar method to Peter in an autoencoder here And in this plot here, you see things that are weird using one method and that are weird using another method. And if they're weird using both, then they're probably pretty weird. And what he was able to do actually was to show that from the simulations, he's able to pick out, there were some interstellar objects in the simulations. He's able to pick those out. There were some asteroids with weird colors that he was able to pick out. And he was also able to find some errors in the way that they set the simulations up that show up in one or other of these parameters. And so they've gone back and fixed some of these things in the simulations as well, which is kind of neat. So it's finding weird things, right? It's finding anomalies. They might not be aliens, you know, it might not be an interstellar craft that's roaming through the solar system, but it's still potentially pretty interesting. And this really recalls sort of some of the early experiments that were done, Jocelyn Bell Burnell's experiments, where they found this kind of weird, regularly pulsing object in surveys that were being done in Cambridge in the 1960s. And they wrote on this chart recorder here, they called this particular source LGM1, so Little Green Man 1 was what Jocelyn and their collaborators called this, because they thought, well, this is really weird. Like, why is the thing pulsing regularly? We now know this is called a pulsar. It's astrophysical. Pulsars are still pretty weird, right? They're the mass of the sun compressed into the size of the Bay Area. They spin as fast as a kitchen blender. And some of them, their magnetic fields are strong enough that if you put them at the distance of the moon, they'd wipe everybody's credit cards here on Earth, which is kind of nuts. So, you know, pulsars are weird. They're, you know, worth investigating. And you know, they're also now kind of probes of other interesting things in astrophysics. So if you find anomalies in searches like this, even if it's not aliens, it can kind of be pretty interesting. I want to kind of wrap things up again by talking a little bit about, you know, we talked about these technosignature searches, and I mentioned biosignature searches going on, you know, on Mars and with instruments like JWST, which is looking for signs of life in exoplanet atmospheres. And that's a pretty hard measurement to make. So we'll go again back to you know, the Drake equation here and think about, you know, JWST that's trying to look for, you know, essentially this number here, and then the technosignature searches. And there's an interesting point that's made nicely in this paper by Jason Wright and collaborators. So Jason also a Berkeley alum here who led this paper talking about the case for technosignatures and why, you know, like if you were sort of betting on, are we going to find biology first or technology, you might look at an equation like this and think, well, Steve, you just told me all of these numbers must be less than 1. So it means, or, you know, less than or equal to 1. So it means there must be fewer communicating civilizations than biological worlds, you know, fewer planets with intelligence than planets with life, fewer planets with communication than planets with intelligence. But even in our own solar system, we know that there is one world that we know of with life, and that's Earth, but there are several worlds with technology. Somebody said Mars is a planet that is entirely inhabited by alien robots, which I think is a good way of thinking about it. When we point the Green Meg telescope at Mars, we see those robots. I mean, they're alien to the Martians if there are any Martians, right? But again, it's our technology. I showed you the point of Voyager 1, we find Voyager 1, right? There are technosignatures all over the solar system, but the only place that we have biosignatures so far is here on Earth. And so technosignatures might be abundant. They might be more because technology can spread potentially more easily than life. They might be long-lived. You know, if we do blow ourselves up, then some of these space probes are going to be going on into interstellar space for long periods of time. They might be highly detectable. So, you know, Tesla mentioned thousands of light years. Those biosignature experiments currently can only be done around a handful of nearby stars, and that there's no real kind of possibility that that's going to improve too dramatically in the foreseeable future, maybe to sort of dozens or even hundreds of stars. And they may be unambiguous. You know, if you get a series of prime numbers in binary, you know, coming from the star Vega, and if somebody else points their telescope at it and sees the same thing, and if that becomes verified, then, you know, that's pretty unambiguous as a technosignature compared to some of these biosignatures, oxygen in an atmosphere, for example, which, you know, might not be quite as convincing. So we do have now, you know, experiments going on at telescopes around the world, radio telescopes and optical telescopes. We're surveying kind of a wide range of objects, including things in our solar system and things beyond. To quote another paper that was really kind of pioneering around the time that Frank was doing those experiments at the turn of the 1960s, from Tony Morrison, the probability of success is difficult to estimate, but if we never search, the chance of success is 0. I mentioned the summer program. Again, if you have undergraduates that you know that might be interested in applying for that, then you can either scan that QR code, take a picture of this, or come and talk to me. And that was exactly 1 hour, and I will not take any questions. Thanks.